Okay, so the first thing we'll cover is the definition of inversion. So, just 1 minute. The inversion is basically a function that maps every point in the plane to some other point. And how it's defined is first uh, you can write it as a function in terms of either a point and a length, which is a radius, or a circle, which is just defined as the circle through this point with this radius. So if we let this point be P, then for any other point, or let's let this point be O. So for any other point P, this function will map P to some point P dash, and P dash will always be on the line through O and P. And this is mapped such that OP times OP dash is equal to R square, where R is your radius. So this has a lot of nice properties. So first of all, by definition, any line through the center of inversion O will go to the same line itself, because for any point it goes to another point on the line. And also this is kind of obvious, but if P goes to P, if P goes to P dash, then the inversion sends P dash back to P because of this. So now we look at what other structures go to. So if you have a point O and an inversion at O, what happens to a line which is not passing through O? Can anyone tell me?
Circle passing through.
Yes, it goes through a circle passing through O. And do you have a proof for this, or do you want me to prove it?
I mean, you can consider the foot of the perpendicular from the circle to the line.
Okay, this point.
Yeah, and then you can construct stuff. It's like easy because we can show that this particular point we have,
Mhm.
if we consider its image,
Okay,
and then we consider the circle through that diameter, that image, that P prime, we can
yeah,
easily show that each point in the line maps to the point in the circle by similar.
yes, sure. So, okay, before this, I just wanted to do one more thing, which I should have done before. It's what happens to uh, just any two random points. So you have your inversion at O, and say you have a P and a Q. And suppose this goes to some 2 points, Q dash and P dash. So what you have here is, you know that uh, OP times OP dash is equal to R square, and that's equal to OQ times OQ dash. So what this gives you is that OP by OQ is equal to OQ dash by OP. And since these two triangles, OPQ and OQ dash P, they have the same vertex angle here, and you also have this ratio, that means they're similar. So what you get there is this angle is equal to this angle, and this is equal to this. So in general, this gives you that for points P and Q and their inverses P dash and Q dash, you get that OPQ is equal to OQ dash P dash. And this is very important, and you should keep this in mind in general. So now let's come to a random line and its image. So what someone had mentioned before about the foot going to the diametrically opposite point, that's also important, and we'll be looking at that very soon. But for now, let's consider um, some random points P and Q on this line, and you have O. So you want to look at um, their inverses with respect to inversion about O. So, okay, first of all, yes, yeah, okay. We'll need one more point because 3 points. Um, yeah. So what we know is that we know that OPQ on this line, this is equal to OPR, right? Because these 3 points are collinear. So now when you do the inversion, what you get is you get OQ dash P dash is equal to OR dash P dash. But this is the property of a cyclic quadrilateral, right? Like these two angles being equal. So this gives you that O, P dash, Q dash, and R dash are all cyclic. So how you prove that any point lies on the circle is you just fix P and Q and you vary R on this line. So that means that any point on this line goes to the circle OP dash Q dash, which passes through Q. And now we come to the center, what happens to the center of the circle. So as before, we know that this is the circle. And let the two intersection points be X and Y. And let the center be some E. So can anyone tell me what happens to the center of the circle upon inversion about O? It's very similar to what was mentioned before. So I hope everything so far was clear. If there's any doubts, please ask.
Inversion about O with what radius? Or does it not matter?
Okay, so the inversion about O sends this circle OXY to the line L. So it's some radius, so it should be radius OX, which is equal to OI. We're just considering the
Oh, okay.
inversion that such that this happens. Yeah. So you can take some time to think about this, and if you get the idea, you can tell me. So far, I just covered the definition of inversion, and we showed that a line passing through the center of inversion goes to itself, and that a line not passing through the center goes to a circle passing through the center. And that means that a circle passing through the center goes to a line not passing through the center. And now we're trying to figure out what happens to the center of a circle which passes through the center of inversion. Yes, the point someone mentioned before, which is the foot from O to this line, let's call it Q, maybe showing what the inverse of Q is might also be useful.
Inverse of Q is the intersection of the tangents from x and y to the circle.
Now, the inverse, we're talking about the inverse with respect to O, not about P. So the inverse of Q with respect to P would be this intersection, but we want the inverse with respect to O. And O is the point that sends the circle OXY to the line L.
Wait, what's the radius? It's the radius OX.
Yeah, the radius should be OX because X is preserved under inversion, right? It lies both on the circle and on the line.
Intersection of the tangents at x and y to the circle with radius OX.
To the circle with radius OX, sure, but can we define that point in some other way?
It should be the what do we say it like diametrically opposite point to O, because that point will be OX 90 degree.
Yeah, exactly. So if you consider this point the antipode of O, let's call it Q dash. We want to show that this is the inverse of P. So we know that OX is equal to OY because both of them have to be the radius of inversion since X and Y go to themselves. So um, since they are equal, that means the foot from O to XY must pass through the center, right, by symmetry. So it passes through the center P. And therefore, if you intersect it with the circle again, you get the antipode. So that means these two are 90. But now, if you look at the similar triangles, um, OXQ similar to OQ dash X,
We can also
then
say it another way, right? Like, if you consider a circle with center O and XY on it,
mhm.
then that implies Q prime X is tangent to the circle because of the 90
Yes,
degree.
sure.
So then that way you're done.
You also get, yeah, you can get this angle is equal to this angle. Yeah, and you can also get it by power of a point using this similarity. So I'll just write it. You get OX squared is equal to Q times OQ dash. Yeah, but these are equivalent. So essentially you get that Q and Q prime are inverses. So I hope this part is clear to everyone. And if there's any doubts, please ask. So now,
No, it's clear.
okay. So now what we do is we consider the inverse of P. So it must be some point on this line, P dash. And we know P is the center of OXY. So what do we know about the lengths OP, OP dash in terms of the other lengths on this line? We know that OP times OP dash is equal to OX squared, which is the radius squared, which is equal to OQ times OQ dash. So from this, can we get something nice about P? Something nice about P dash.
Um, the circle passing through P dash P and X, OX is tangent to that circle. Right?
The circle passing through, are you talking about this circle?
Yeah,
This is tangent to, yeah, this is tangent to OX and OY. Mm,
I meant like Q dash goes to Q because that circle goes to that line,
yeah.
and O Q dash, so Q dash goes to Q. And as it is the involution, so Q goes to Q dash.
Yeah, we were showing that itself. Like you have to show one of them first, right? Like either Q goes to Q dash or Q dash goes to Q. So
Y-
I think you meant Q dash goes to Q is already implied because the circle goes to the line.
okay, yes, that is true. Yeah, you just intersect that. So essentially, you just need
Yeah.
that P lies on the diameter. Sure. Yeah, you need that Q lies on the diameter. Yeah, that is true. Okay, so what do we know about these lengths? Can we try using that P is the midpoint of OQ dash? Because P is the center and OQ dash is the diameter.
Select use the midpoint of OP prime.
Yes, exactly. So I'll erase this for now. And yeah, we have OQ dash is equal to 2OP. So plugging it into this, what we get is OP dash is equal to 2OQ. So P dash is the reflection of P over OQ, essentially. Sorry, P dash is the reflection of O over Q. Yeah, because this implies this, yes. So essentially what we showed is if we have a circle passing through our center of inversion O, then what is the inverse of the center? The inverse of the center is you take the inverse of the circle and you reflect O over this inverse. And this is the inverse of P. So I hope this is clear for everyone. And now we move on to the next thing. Okay, so what happens if we have a circle which is not passing through the center? So you have O, and then you have some random circle. Can anyone tell me what this circle goes to?
Another circle.
Yes, and can we prove that?
We can take the points which like we can first draw the center of the circle and draw the points which are the intersection of the line O and O1. Let's say O1 is the center.
Okay.
Okay. Yeah, so the intersection of these, let's say AB.
Sure.
Yeah, so first of all, we can say that A and B will also, sorry, A prime and B prime will also lie on this line.
Yeah.
And now we can take another point X on the circle. We know that AB is the diameter. So from that and the cyclic properties, we can conclude that it is another circle. Now, yeah, we just draw X prime somewhere.
Mhm.
And we now show that X prime, B prime, A prime is always a circle with diameter A prime, B prime.
Yes. So
Like
essentially we want to show, yeah, go ahead.
no angle AXB that's equal to angle AXO plus OXB.
Yes.
So that's like angle X prime A prime O plus angle OB prime X prime.
Yeah.
Um,
You're
plus
almost done.
O.
Wait. AX. Wait, this is OX, this is minus, right? This is
It is this directed?
Yeah, this,
okay, sure.
but like we can keep it minus, I guess that
Yeah.
works.
Okay, let's write everything like starting from O. I think that'll make it
Yeah,
simpler. So AXB is equal to OXB minus OXA. And now applying the angle property we learned, it's O dash, sorry, OB dash X dash minus right. So it's this angle minus this angle, and so that must be this angle over here. But we know this is 90, and therefore this must also be 90. So for any point, in fact, I think this, yeah, for any point on the circle, we get that b dash x dash a dash is 90 for any point x on the circle and its inverse. So they must all lie on the circle with diameter a prime b prime. And therefore, the image of any circle is also a circle. And this also proves that the centers are collinear, but that doesn't mean that that O1 goes to O2. It just means O1 goes to some point on this line. So yeah, keep that in mind. So now I want to look at a special case, which is when we have tangencies. So suppose we have, say, two tangent circles. Can someone prove that their inverses must also be tangent? It's a very simple like proof.
With respect to which circle?
So any inversion, like you just invert about O,
Okay.
and their inverses go to some two other circles. Can we have like a very straightforward argument as to why they must also be tangent?
And the common point has to
Yeah,
lie on both
exactly.
sides.
Yeah, so if they have exactly one common point, then their inverses must also have one common point, because if they have two common points, then that doesn't make sense because their inverses must also be two common points. So yeah, just looking at the common points gives you that tangencies are also preserved. And similarly, if say a circle and a line are tangent and the line doesn't pass through O, then their images will be some circle passing through O, some other circle, and they'll also be a tangent. So any sort of tangency is preserved. Okay. Now we'll do one more thing before moving on into like configs. So let's say I'm inverting about a point O with some arbitrary radius, and there's two lines, say L1 and L2. And they make an angle of theta. And what I want to show is that, so their inverses will be two circles. And I want to show that the tangents to these circles at the common point, they also form an angle of theta. This is what I want to prove. So let's say L1 goes to omega 1, L2 goes to omega 2. So you can take some time to think about this and let me know if you have any ideas.
By the way, the lines are intersecting at only. No, no, okay, it's fine.
So one of the intersections
Yeah,
should be
one of
O.
them is the center, yeah.
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 Wait, one of them is a point at infinity.
No, no. One of them is the inverse of this point. So if this point is P, one of them is P dash, and the other intersection must be O, because both of the circles must pass through O.
Oh, okay, yes.
Like we can let Q be a point on the arc P prime O and omega 1, like a minor R. And we can let R be a point on the other circle. And like we can like try to find angle QOR, and then like try to bring Q and R closer to O and see like what happens.
Mm. Yeah. So where do you want R? Do you want R like here?
No, like on the minor.
Okay.
Um,
Okay. Sure.
and I guess like this would be equivalent to finding like the angle um between the tangents at P prime, right?
Yeah.
Um,
Same thing.
so I guess we could find angle Q P prime R.
Q
Um,
P prime R. Sure. So Q would be somewhere on line 1. Let's say it's here. R would be somewhere here. It might not be on the right side, but we'll figure that out. So you want to find um so let's
angle.
call this R prime. Yeah. Yeah, go ahead.
So like angle Q P prime R, that would be like angle Q P prime O plus angle O P prime R. Okay.
Yeah, I'm
Um,
just using prime for the second one. Yeah.
yeah, and that is angle uh, PQO plus angle RPO. Wait, no, sorry, angle PRO.
Yeah, sure.
Can you explain how did we got these angle conditions?
Okay, so were you there when we proved that in general, for some inverses P prime and Q prime, we have this equality, OPQ is equal to OQ prime P prime?
Yeah.
Yeah, so we're just considering random points on these circles and applying that same thing.
Yeah.
So this is just implied directly, and this to this we are getting using that property. Okay.
Yeah.
Okay. So we have that this is PQO plus PRO, and this is actually like 360 minus theta minus angle QOR, just 360 minus theta minus angle Q prime OR prime.
I don't think we need to do this, right?
Yeah, you don't have to.
Like we can just draw the lines through a parallel to like L1 and L2, and we claim these two lines are the tangents.
Okay, sure. And how would you prove that? So
So like clearly like L1 must go to a circle and L2 must go to a circle. And
yeah,
since L1 and L2 like since L1 and the tangent like passing like call the lines through O parallel to L1 and L2 be P1 and P2.
okay. So P1 and P2.
Now clearly L1 and P1 intersect only at the point at infinity, which is mapped to the center.
Yes.
Oh, so like they'll be tangent at O itself and that finishes because two parallel lines it forms a parallelogram which is again theta angle.
Yes, okay, that works. So wait, so we get that the image of P1 is some circle passing through
Can
tangent
you
to this
explain
line.
this proof again? The one Nishant gave.
Uh, would you like to explain it again, Nishant?
Yeah, I can try. Okay. So what we know was that L1 and P1, like the
Yeah.
line, like L1 goes to a circle, and clearly L1 and P1 intersect at the point at infinity along the two lines.
Can you
Yeah.
just pinpoint the definition of P1 and P2 again?
Okay, so we're defining P1 as the line through O, which is parallel to L1. So L1 is somewhere here, and P2 we are defining similarly. And we're just claiming that these are the tangents. So actually, we just need one of them.
Yeah.
Yes. So now P1 must now since L1 and P1 go like meet at a point at infinity, we
Yeah.
know that all points at infinity like map to the center O of inversion.
Yes.
So like
That.
clearly like the two circles, like that line, that circle and the thing only meet at O. There's only one intersection point and that suffices
Yeah.
because it's a
Okay.
tangent.
Yeah. That makes
So you are
sense.
saying the inversion of L1 coincides with P1 or what?
No,
Mm,
the inversion of L1 coincides with a circle which is tangent at O to P1.
Okay. Oh, alright.
Okay, so what you're saying is initially you have L1 and P1, they are parallel, so they have no points of intersection in the real plane. But now when you invert, L1 goes to omega 1 and P1 goes to itself. So suppose they're not tangent, then they have like some point of intersection other than O. But that's not possible because that point does not have an inverse. Therefore, they must only intersect at O.
Alright.
Okay, that makes sense. Another proof is just looking at the centers and then computing the tangent angles using like tangent secant theorem. You can try to work that out yourself. But yeah, this proof also works.
It's like
So
we are proving like P1 and P2 intersection is the same as them, and we know that we prove that P1 and P2 are actually those tangents we were trying to.
yeah, we prove that they're the tangents and they're both passing through O, and therefore they must make the same angle theta at O.
Okay.
Okay. So a specific case of this is if you have two perpendicular lines, then the circles they go to will be orthogonal. And this is actually very useful. Like this has shown up in problems. So say for example, you're inverting about the in circle and then you want to deal with the altitude. Something like that would correspond to some circles being orthogonal. So just keep this in mind. Okay. So now we'll go to some specific types of inversion which are useful.
Could you repeat the orthogonality thing?
Yeah, sure. So we prove that if two lines form an angle of theta, the tangents to the circles they go to under inversion. The tangents at the common points also form the angle theta. So now if the angle is 90 specifically, then these angles must also be 90, the angles of the inverses. And that is equivalent to the circles being orthogonal, right? Yeah, that's all. Okay. So now let's go to some specific inversions. So the first one is, okay, let's say we have an orthocenter configuration. So have the feet of altitudes. And now can someone tell me an inversion at A, which is useful in this situation?
Root AH into AD.
Yes. So the inversion with radius root AH times AD. So this means it's swapping H and D. And we know from power of a point on the cyclic quadrilaterals HFBD and HECD. From this, we know that AH times AD is equal to AF times AB, which is equal to AE times AC. And this also means that along with the swap of H and D, we also swap B and F and C and D. So this is one thing you can do. So can anyone tell me where the 9-point circle will go? So it's the circle passing through the feet of altitudes and the midpoints of sides.
The circle.
Yeah, because wait, no. See, D will go to H. E will go.
Circle
Yeah, it
BHC,
goes
I
through
think.
BHC. Yeah,
Yeah.
goes through BHC. And yeah, that's the main things. And you can figure out where all these other circles go. So, for example, ABD will go to line FH, and ACD will go to EH, and so on. And the second inversion that's useful in this case is inversion about H with radius root HA times HD. But you're not just doing this, you're also reflecting, so that A will go to D and so on. So when you define inversion, normally you define the inverse of a point to be on the same side of the center as that point. So P dash and P are on the same side of O in this case. But in certain cases, you'll want to reflect the inversion about O. So it's the same thing, but the inverses are on the opposite side. So when you do this for the orthocenter case, does anybody like notice any nice things apart from the obvious one, which is A swaps with D? Similarly, what else do we know will swap?
B and D and C and A.
Yeah,
F and
similarly,
C and B.
yeah. And this is because HA times HD is equal to HB times HE and so on. Again, because of power of a point. So here, can someone tell me what the 9-point circle will go to?
Circumference.
Yes, here the 9-point circle will go to the circumcircle. And in fact, M will go to, so M, we know that M lies on the 9-point circle, right? So
Moves on A anti-close.
yeah. So no, okay. Because we're reflecting, it must go to a point here, right? So in
Q
fact, this
Point.
point.
is the Q
Q
point, yes. So M is a point such that, so we know HDM is 90, and M goes to this intersection with the circumcircle, and therefore we know that if we call the intersection Q, we know that HQA is 90, because the same angle conditions hold. So this is like another proof that QHM, where Q is the Q point, are collinear.
Wait, how do we decide which side does it go?
In this case, we're choosing to reflect. So in this case, it always goes to the opposite side, whereas normally it's always on the same side.
Yeah,
So
okay.
yeah, here A and
And
D are opposite.
reflecting about,
The center of inversion.
okay, okay.
Yeah. Okay. So yeah, that's like another proof of this Q point property. Now the third thing I wanted to look at was in-center inversion. So if you have in circle, can anyone tell me what ABC will go to when you invert about the encircle.
Midpoint
Yes, T
triangle.
and ED.
Sorry, what did you say?
Midpoints of EFE.
Yes. So each of these will go to the midpoints of these corresponding tangent chords. And the reason for that is, suppose you join EI, this angle is 90. You know that these angles are also 90.
What is
So
the ratio here?
the radius of the encircle, it's just inversion about encircle.
Okay.
Yeah. So if you call this point, say, P, then by similar triangles slash POP, you have IP times IA is equal to IE squared, which is equal to R squared. So P must be A's inverse, right? So similarly, you get that these 2 points are also the inverses. So that means that the circumcircle of ABC goes to the 9-point circle of DEF. So now if we take this circle passing through AFIE, we know that it must go to line FE, right? Just by the first thing we proved. So let this second intersection be S. Okay, so do we know the inverse of S?
Fifth foot of altitude of the
Yes.
EF.
Foot of D onto EF.
Yes, perfect. Just okay. And why is this true?
Because like 9-point circle passes through the
Yeah.
altitude.
Yes. So you know that S is the intersection of ABC and um, AFE. Therefore, S dash must be the intersection of the inverses, which is the 9-point circle and FE. And we know it can't be, so there are 2 intersection points. One is the midpoint and one is the foot of altitude. We know the midpoint's inverse is already A, so it must be the foot of altitude. And if we call that S dash, we know that I, S, and S dash must be collinear. And this point, as it's called the Sharkey double or spy point, just for information. It has a lot of other properties as well, like you have that SDS collinear with the midpoint of arc of ABC of BC and other properties like that. You can try proving this yourself. And now we move on to, if this is clear to everyone, we move on to the last type of inversion I'll be doing here, and that is root BC inversion. So does anyone know what this is?
We take the radius root AB into root AC and then reflect over the angle bisected.
Yeah, perfect. So what we do is, this is inversion about A with radius root AB times root AC. So first, if we just do this, that means that B goes to some point B dash over here, and C goes to some point C dash, such that AB times AB dash is equal to the square of the radius, which is AB times AC. So that just means AB dash is equal to AC. And similarly, AC dash is equal to AB. So basically, this is isosceles and this is also isosceles. So now what we do is, we want the length that is length AC. We want it to go here. So what we do for that is, we reflect both of these points about the angle bisector of A. And what happens if we do that? Since this triangle is isosceles, B dash goes to C and B goes to C dash. So essentially, we did two steps. We did this inversion and then we did reflection about A angle bisector. And what happened here is B went to B dash, which then went to C, and C went to C dash, which then went to B. So basically, B and C got swapped. And in general, what this means is if you have some line passing through A, it goes to the reflection about the angle bisector because it goes to itself and then it gets reflected. So can we like think of any nice properties? So can someone tell me where the circumcenter goes, for example? You have the circumcenter O. Remember what happens to the ratios and also think about what we're doing here and try if you can figure out where O goes. Okay, so before that,
It goes to edge, right?
um,
The line is the line passing through edge.
O does not go to H.
At
So
least it
A,
goes to the line passing through edge.
yes, it goes to some point on this line. Yes. Okay, before that, can we figure out where the antipode goes? So we know that the circle ABC, this must definitely swap with line BC because B and C just switch. So based on that, can someone tell me where the A antipode goes?
Section of A dash.
H cap BC.
Yes, perfect. Because this point is on the circumcircle. So the inverse after reflection must be on line BC. So it must be this point, say D. Now O is the midpoint of A dash. So
It would be like the reflection of, so like it would be like the reflection of A about BC, right? 'Cause,
yes, yes, it's very similar to the
uh,
thing we did before. Yeah, go ahead.
okay, cause like 2AD into R is equal to AB into AC.
Yeah, perfect. Because of the equality with the radius squared. So essentially, we know that A dash is equal to no, A dash times AD is equal to AO times AO prime, where O prime is the inverse. And we know that this is equal to 2AO. So cancelling, we know that AO prime is equal to 2AD, very similar to what we did before. So the inverse of O is the reflection of A over BC. And so by this similar thing, we know that the summedian, so summedian is the line passing through A and the intersection of tangents. This will go to the median. And similarly for all the isogonal lines, they'll go to each other. So I hope this was clear. Does anyone have any questions about any of these?
Where does the midpoint go of BC, midpoint of BC?
It goes to the intersection of the
Yes.
median with the
Yes, so the midpoint of BC must go to some point on the circle, but it must also be on this median, so it must be this point, say K.
Oh, yeah, okay, yeah.
Yeah, and the midpoint of AK would go to the reflection of A over M similarly. Okay, so these were the main types of inversions I wanted to cover. They're not the only types, like in the sense that maybe some inversion in a problem won't fall into one of these, it might be more random. But in general, this is something you can try in each of these configs if you get stuck in a problem like this and the angles seem good enough. This is always something that could be useful. So if all of this is clear, we'll move on to the problems. They're not very difficult, but it'll take some time to get used to inverting. So this is the first problem. And if you've seen the problems I'm doing, you can ask me for more problems and I'll send them to you. So just try this for some time and please feel free to let me know if you have any ideas.
I think I am done. Should I say the solution or can I try another problem?
I can send you another problem to try. We'll wait for a few more minutes and then you can say
Sure,
the
sure.
solution.
Yes, thank you.
I believe I'm done as well.
Okay, I'll send some problems in the chat for you to
Okay, yeah,
try.
that will do.
Okay. Okay, we'll wait for a few more minutes and then one of you can share your Okay, a lot of people seem to be done. So, Nishant, would you like to give your solution? Or someone else as well? Anyone can.
We take circles at ABCD with radius EA, EB, EC, ED.
Yes, so we notice that these are equal because of the reflections. So each of these is a circle with centers at ABCD, yes. So each of these have center A, B, C, and D respectively. And you get the equal lengths from the reflections. Yeah, go ahead.
Now we invert with arbitrary radius at centered at E.
Yeah, so you have a bunch of circles passing through E, so inverting through E is sort of motivated here. So then what do you get?
So that becomes like the radical axis of the circle.
Yes, true.
What do you mean by radical?
Like,
The
just
circle
an
map to
instant.
those lines is what.
Yeah, okay, the circles don't map to the radical
They
axis.
form the quadrilateral XYZ W.
How are they mapping to the radical axis?
Like the radical axis remain preserved. I think that's what he meant. But anyway, do we see what happens to the circles themselves?
They become quadrilateral XYZ.
Yes, so we want to look at the new quadrilateral essentially. So if you look at the circle passing through A, we know that it's tangent to BD, and we know that we know that BD goes to itself. So try to think of something else you did before, sort of similar. Where would a tangent circle go?
Wouldn't this power of point work here?
Power of a point with respect to E.
Yeah.
We don't know that ZEX and WEY are collinears.
Okay. Yeah.
It will go to some other two circle. Wait, but it will go to line. Because it's
Yeah, these circles will go to lines. But what kind of lines?
Like which circles are you talking about? The greens one, right?
Yeah, the green ones. Let's call them yes.
Like they will be if we take a random circle omega centered at E, the circle will be the radical axis of omega and omega A.
Which circle will be the radical axis of omega
The
and
omega
A?
A circle, here,
Okay.
right?
Okay, we know that it goes to like some line, but like what more do we know about this line? So okay, let's say this is LA. We know omega A goes to LA. We know that BD goes to BD itself. And these two are tangent. So what do we know about these two lines then?
Wait,
They're
why does
only intersection. Yeah, go ahead.
no. Okay, never mind.
Okay. Yeah, so before we did something like if you have a circle tangent to a line, and then you invert about this point of tangency. The line goes to itself, but this and the circle also goes to a line. But can they have an intersection point? Is that possible?
No, they would have to be parallel.
Yeah, they have to be parallel because their only common point was O. So they can, when they both go to lines, they cannot have another common point because that does not have an inverse. So they have to be parallel. So this means that LA is parallel to BD. And from here, can we finish?
It
We
will
get
map
all,
to a rectangle, right?
yeah, exactly. So we have all the similar parallel lines. So this means that LA and omega LC are parallel because they're both parallel to BD. And the other two would be perpendicular to them because AC and BD are perpendicular. So W, X, Y, and Z goes to a rectangle. So when you invert back, so the rectangle is obviously cyclic, right? So when you invert back, it must invert to a circle. So that's why they're cyclic.
Yes. This makes
Okay. So I hope everyone understood this. So rectangle and therefore they're
I have
cyclic.
one question.
Yeah.
Here the circles are mapping to LA, LB, LC, and LD, right?
Yes.
And then we're showing, and how is LA intersection LB
Oh,
Z or the okay,
LA
it's the
intersection.
image of Z. Okay, yeah,
Yes, yes. These are the images.
yeah.
Yeah. Okay. Let's go to the next problem. Uh, Yes, we are asked to prove that two angles like about the top vertex. So in this case, the top vertex is C. We are asked to prove
So,
that two such angles should be
so
equal.
I think root BC inversion work
Yes, because it suffices to show that one of those lines
because
goes to the
because
ellipse.
the tangent circle will be maps into the x circle, ax circle.
Yes. So we have this tangent circle. And the first step would be to show that this is to like figure out where this maps to. So if we
This
want to,
P should be the intersection of the midpoint of arc BAC and the incenter of ABC.
yes, that's a property of the mixed linear point. So um, this would be the midpoint of this chord would be the incenter, and this intersection would be midpoint of arc BAC. You don't really need that in this problem, but it's good to know. And yeah, we want to prove that this tangent circle goes to the AX circle. So does anyone have a proof for that?
Q also lies on this line, PIN,
Q.
because it's
Mm,
tangent and by like what do you
yes, by
by
homotopy.
yeah.
Yes, this point would be Q.
You know that there is only one intersection of P with the, like P is the common point, only common point of the two circles.
Yeah.
So P will go somewhere to B, such that another inverted circle will be tangent to BC.
Yes, so the image of the circle will be tangent to BC, and it would also be tangent to CB and CA.
And
This
similarly, we
will
can
be the perpendicular from x center to BC.
Yes, so okay, we know that the image of the circle is tangent to both AB and also CB and CA because they go to each other under, in this case, root AB inversion. And so actually there are two options. You can have the in circle or the X circle, but uh, the tangency point of the in circle, like it will be on this side of the midpoint, right? It'll be somewhere here. And so these two can't be reflections. These two green lines can't be reflections about the angle bisector because I is on the other side. You can do some argument like that. So that means that it can't be the in circle, so it must be the X circle, which is tangent to all these lines. And so you have some point here. Let's call it R. So P and R swap under root AB inversion. Does everyone see why? Because omega must go to the
Because it's tangent
swap.
to the circumcircle, which will go to line BA.
So why should omega go to the x circle?
Because since omega is tangent to CB, CA, and the circumcircle, the image should be tangent to CA, CB, and the line AB. Because the circumcircle goes to AB.
Goes to AB. Yeah, actually.
Yeah, so you have two options, the in center, the in circle and the X circle. And it's easy to see it can't be the in circle, so it has to be the X circle. So now you have some point R, and you know that PCB is equal to RCA. So you just want to prove that Q lies on CR.
This is true by homotopy, I think.
Yes, because you know that these two lines are parallel. So now you're just looking at the circle tangent to this line and CA and CB, and now and you're also looking at the circle tangent to this line CA and CB, so they must be homothetic at C. So therefore you have CQR, and then you have ACP is equal to RCB, which is equal to QCB.
How did you prove CQR is collinear?
You look at the homothety sending omega to omega A.
Okay.
So C is the center of homothety. And the tangency points go to each other because the homothety will also send these two lines to each other. So I hope everyone understood this. If you have any doubts, again, obviously you can ask.
How is the angle ACP equal to RCP by the way?
Okay, because we know that P and R are inverses upon root BC or root AB inversion.
Yeah.
And that means that CP and CR are reflections over that angle bisector of BCA. So this angle is equal to this angle. Therefore, this angle must be equal to this angle.
Okay, yeah. Yeah.
Yeah. So our next problem is this one. It's similar type of problem. The source of the previous problem is EGMO 2013 problem 5, I think.
The game seems motivated by root BC.
Yeah, again, it looks like we could use root BC here. So if
Root
you get,
BC sweeps like D, E, and F to the midpoint.
yes, so we want to show that F goes to the midpoint and upon root BC, so F will go to the point on AC such that EM is perpendicular to AC, right? Because the angle EMD should be 90. And this is the midpoint, right? Because E is the midpoint of arc AC, so the foot from E to AC should be the midpoint. Does everyone see that?
Yes.
Yes.
We could
So
also say like this is C-median point. So its reflection is like the line AM, and as it is lies on ABC, it should be lie on the BC. So it is here.
yes, so because BF and BM are like they swap because of root BC and BM is the median, BF must be the median. These angles are equal.
But why should
And
D cut AC at the midpoint?
because it's the circle with diameter DE, so it cuts AC at the point M such that EM is perpendicular to AC.
Yeah, yeah,
So
okay, got it.
E
Yeah.
is the midpoint of it. Yeah. Okay, that was fairly simple. Um, yeah, we'll do one more problem.
Wait, 1 second. In the previous problem, like, why
Yeah.
does how do we get that EMD 90? Like, we know that's true, but like, how do you know F goes to M? I don't get that.
Because like if you consider the image of F, so it must still be on the circle with diameter D, right? Because D and D go to each other, and the
Yes, but
center
how
of
do
the
you know the
circle.
circle is fixed? The D circle is fixed. Oh
Okay,
yeah,
so
we
like
just consider the intersection. Yeah, correct. Yeah, that's correct.
okay, yeah. So just to clarify for everyone, the DE circle is fixed because we know that the image of the circle must also pass through D and the center must also lie on this line. So it must be the same circle.
So F mapping on the circle D, why does it fix it? Okay, because it should also lie in BC. Okay,
Yeah,
yeah.
exactly. Okay, so we'll do one more problem. It's actually very similar to the problem, like two problems back.
So it is sufficient to prove ABC median.
Yes.
I think root half BC inversion will work.
Yes, you can do that. You can also, yeah, I think root BC would also work. Um, but yes, root half BC is essentially using the radius this, and where would this send the midpoints?
And the midpoint to BC.
Yes, so M would go to C. So here we're just doing the same thing but scaled by a factor of half or a factor of 2 depending on how you look at it. So here instead of M going to like instead of B going to C, you have M going to C and N going to B. So where would the circles go? So A, B, N goes to C, M, right? And ACM goes to BN. So what does this become equivalent to?
So the intersection will be the centroid.
Yeah, so it'll go to BN cap CM, which is the centroid, say G.
So which is clearly passes through the midpoint of BC. AG is passes through the mid.
So AG passes through M, and that means that, so P goes to G, and that means that the inverse of G lies on the median. Right, so again, we're done. There is one more
Sorry,
thing.
where do the intersection of the tangents go?
So intersection of the tangents, it lies on the median, right?
Yes,
Um,
I
so,
see.
and
Yes.
median is reflection of median over angle bisector.
Right. Yes. Okay.
Yeah, that's right. Okay. There's one more problem I wanted to show you. This is
I had
probably,
one question. In
yeah, sure.
root BC, like not about this question, but
Mhm.
in root BC, do you know where does G go, like explicitly?
G would, okay, so in normal root BC, M would go to the reflection of A over C. So let's call this um, AC, and N would go to this reflection, which is say AB. And now G is CM cap BN. So that would be basically the intersection of circles AB, AC and AC, AB. So like this one and this one. So it's some point here and it should lie on the median.
Okay, got it.
Yeah. Okay. So there's one more problem you can try for some time. It's probably too long to finish within the class, but the main point is just to identify where the points go upon inversion, and then normal, like synthetic, would work. So let's just try to get the inverted problem, and then you can try that yourself. So does everyone understand how X and Y are defined? So you essentially take the bisector of this IDB angle and this um, AIEA angle, and you intersect those to get x, and similarly you get y. So what do you think is like the most natural inversion in this one?
In circle inversion.
Yes, in circle inversion. So now what happens is A, B, and C go to the midpoints of the in-touch triangle. So where would x and y go? Let's just draw it from the perspective of D, E, F. So I'll write the angle conditions for x. You can obviously rephrase it as IDB is 90, sorry, 45, and IEX, yeah, sorry, this is x, and IEX is 45. So when you invert, what happens to these angle conditions? What do you get? Can someone tell me? So IX prime D,
IXD will be equal to 45 and I x dash e will also be equal to 45.
yes. And this means that what would you get dxe to be equal to?
90.
9. Yes. Um, okay, so where would x go then? Wait, so in the original figure itself, can we say anything about x? Okay, we can't really say anything about xi.
If we take a circle centered at the midpoint of DE, x dash will lie in the center.
If you take a circle centered at this point, where should x dash lie?
Centered at the midpoint of DE,
Mhm.
then x dash should lie on the circle with like
Yeah,
a diameter as DE.
yeah, that is true. So we can do that. And is there something we can do to figure out exactly where this would be? Okay, in the original diagram itself, do we know something about, can we say something nice about
So x
xi?
dash I is the angle bisector of like dx dash e, clearly.
Yes.
And since that is true, that means ix dash passes to the like midpoint of arc DE. Like I don't know which side, but like midpoint of arc DE. So like midpoint of arc
Yeah.
DE in that circle, that implies like IC dash intersection DE, the DE diameter circle should be x dash. One of the two
Yes. So
intersections.
okay, so like You can also say that XC and XD are similar, like they're symmetric with respect to quadrilateral IECD, right? Because this is like symmetric here, and now you're just taking equal angles over here, right? 45 and 45. So because of that, XIC should actually be collinear. Therefore, X should be one of these points. And before, we know that X was outside the encircle, so when you invert, it must be inside. So the new X must be this point. It's essentially because XIC is the perpendicular bisector of DE. So this fine with everyone?
Yes, sir. Similarly, we can find y dash as well.
Yes. So basically, X dash is the point such that it lies on the circle with diameter DE, and also it lies on the perpendicular bisector of DE. So this is 45, this is 45, and this is 90. And similarly, you can find y, and then it becomes a much simpler problem. So there are many things. So you can invert again. There's some solution I found which has like 3 inversions in total. Or you can also do synthetic. So this is the main thing you need to do first. Okay, so these are all the problems for today. If anyone has any questions, you can, about like anything we covered, you can ask right now. If no questions, I'll stop.